Welcome back to the Deep Dive. Today we're tackling a request that really gets into some extreme technical precision.
It really does.
We're doing a deep dive into the microscopic details of setting up a specific medical procedure, the meticulous prep work for an esophageal stricture dilation. And for this, we're pulling our information from some excellent instruction provided by Dr. G.S. Raju's YouTube channel.
Yes. Specifically, his video on the stricture dilation balloon setup. It's fantastic.
So clear.
That's right. Our mission today is to, synthesize that preparation philosophy. We're not just talking about the high-level goal.
No.
We're talking about the precision required by the assisting team, the exact setup, the sizing, the safety checks for all the equipment.
Okay, so let's unpack the problem first. An esophageal stricture is basically a narrowing of the food pipe.
Right. Makes swallowing difficult, sometimes impossible.
And this balloon catheter method is designed to gently expand that narrowed passage. So what kind of strictures are we usually dealing with here?
Well, they generally fall into two categories. You have your simple ones,
Okay.
things like Schatzki's rings, maybe some thin esophageal webs. They're usually a bit easier to treat.
And then there's the other kind.
And then you get the complex strictures. Those can be caused by severe peptic reflux, previous radiation, or even, cancerous growths.
And I imagine when you're dealing with those complex, scarred-up strictures, the safety requirements they escalate immediately.
They absolutely do. While a simple stricture might just use a standard balloon catheter, the source material is very clear on this.
Which is?
For complex cases, stability is everything. You really want to use a guide wire-assisted balloon catheter.
So if you picture this stricture as this kind of long, scarred tunnel, the guide wire acts like a railway track.
That's a perfect analogy.
It just guarantees the balloon goes exactly where it needs to.
It's all about control, preventing any unnecessary damage during placement.
Right. This brings us to what you could call the first pillar of successful dilation: planning and innovation.
Yes.
Before you even touch any equipment, the assistant has to consult the endoscopist. What are the key planning takeaways there?
Planning is, it's non-negotiable. First, you have to know the required starting size.
Okay.
These can range from, say, 6 up to 20 millimeters. But the really critical logistical part is this. You must have at least 3 sizes higher than that starting balloon available in the room.
So you're ready to go if the first dilation is successful.
Exactly. You can immediately step up the sizing without any delay. It might even reduce the total number of procedures the patient needs over time.
It makes a lot of sense. So having those sizes on hand is key. But the technology itself is what's really fascinating, especially these controlled radial expansion balloons, the CRE balloons.
This is where things get really interesting from an engineering standpoint. You have your basic fixed-size balloons where one inflation gives you 1 diameter.
Simple enough.
But the CRE balloons are marvels. A single balloon can achieve several different diameters. For instance, it can go from 6 millimeters up to 9 millimeters in the same session.
Just by adjusting the pressure.
Just by adjusting the pressure dictates the size.
So it's completely dynamic.
Right.
We hear the term manometric pressure a lot here. How should we, define that for the listener?
Manometric pressure is simply the measure of the fluid pressure inside that balloon.
Okay.
And for the assistant, the reading on their syringe device is the critical variable. When the endoscopist asks for, say, a 7 millimeter dilation,
The assistant has to apply the exact pressure to hit that 7 millimeter diameter. No more, no less.
precisely, the pressure reading is their proxy for the physical size of the balloon inside the patient's body.
Got it. Okay, now that we understand that CRE innovation, let's talk about the physical setup. What's on the checklist?
You've got 4 core components. First, the specialized balloon dilation catheter itself.
The part that goes in the scope.
Exactly. Second, the inflation device, which, people might call the pump handle or the gun.
Right.
That's what controls the fluid. Third, you've got the syringe with its integrated manometric pressure gauge.
And that's where the fluid is held.
And fourth, just your necessary supplies. Sterile water to fill the syringe, some lubricant, and gauze to help the catheter slide smoothly down the endoscope's biopsy port.
Let's focus on that inflation device for a second, the pump. You're saying the entire safety of the procedure really rests on the assistant mastering its 3 handle positions.
Absolutely. The handle has a critical locking mechanism that determines its function.
So position 1 is inflation.
Correct.
You lock it in that direction, you pump the handle, and it pushes fluid from the syringe into the catheter, expanding the balloon.
That's it. Then you have position 2, deflation. Locked there, pumping the handle does the reverse.
It sucks the fluid and any trapped air back out of the catheter and into the syringe.
Which is vital for collapsing the balloon when you're done.
And then position 3, neutral. Why is that position so important? Why can't you just leave it in deflation while you're, say, connecting the catheter?
That's an excellent question. The neutral position is your safety setting. It locks the whole internal mechanism, so you can make adjustments like sliding the syringe in, securing the clip, screwing on the catheter without accidentally applying any pressure or moving any fluid.
It prevents any accidental inflation or deflation while you're still putting the system together.
Exactly. It maintains the system's integrity.
Okay, so once those handle positions are understood, we get to the most meticulous part of this whole thing, the air and fluid management.
Right?
And the critical principle here is the complete elimination of air.
Precisely. Any air trapped in that system, it compromises the accuracy of your pressure reading, and worse, it introduces the risk of an air embolism.
Which is incredibly dangerous.
So we have to perform 2 distinct, absolutely non-negotiable air expulsion steps.
Let's walk through the first one, clearing the air from the syringe reservoir itself.
Okay. First, you mount the syringe while the handle is in neutral. Then you switch the handle to the inflation position.
And you pump it while the syringe is still dry.
Vigorously. This expels all the air that was initially trapped inside that syringe chamber.
And once that air is out,
You switch to deflation, you put the tip in sterile water, and you draw the fluid up precisely to the 35 cc marker.
but even after that, you're still going to have some little residual air bubbles in the liquid, right?
You will. So now we address that. For this second check, you angle the entire device up.
Up.
Then switch back to inflation and pump just slightly. This lets any of those last bubbles rise and get pushed out the tip. You're left with a syringe full of just pristine, air-free fluid.
Exactly. 35 cc of pure fluid.
Ready to connect.
Okay, so now the pristine syringe is screwed onto the catheter. But we're still not done. We haven't checked the catheter channel itself.
Correct. And that is the second major air expulsion step. The catheter channel is just full of ambient air until we flush it.
So how do we do that?
To do this, we now switch the device to the deflation position, and this time, we angle the device down.
So angle it down this time versus up for the syringe check. Why the difference?
Well, when you angle it down and pump in deflation, you're actively sucking any air out of that catheter line and back into the syringe.
Ah, so you're using gravity to help pull the air out.
Exactly. You're using gravity and the negative pressure from the pump to maximize air removal from that distal line. You pump until absolutely nothing more comes back into the syringe.
And only then.
Only at that point is the entire closed system syringe and catheter completely air-free and ready for use.
The attention to detail in that dual flushing process, it really highlights the philosophy here. It's all about patient safety.
It has to be.
So the system is prepped. The endoscopist has the guide wire in place. The balloon is centered in the stricture. Now it's time for the actual dilation.
Once placement is confirmed, often with fluoroscopy, the assistant switches the handle to the inflation position.
Okay.
And they begin to pump slowly, very slowly, until the desired pressure is achieved. And it is paramount that the assistant communicates the pressure reading and the resulting balloon size to the endoscopist.
So the assistant isn't just operating the pump. They're the primary monitoring station.
Absolutely. They're also responsible for timing the duration of the dilation, which is usually held for 1 or 2 minutes, depending on what the endoscopist wants.
Constant communication is key.
It's everything during that phase.
Okay, time's up. We now hit maybe the most crucial point of the mechanical operation, the deflation. The source material is adamant that this has to be 100% complete.
It must be. Or the procedure fails right at the removal stage.
So what's the process?
The assistant switches the handle to the deflation position and pumps until absolutely nothing more is being sucked back into the syringe. They have to ensure that balloon is totally collapsed.
And the why here is just, it's terrifyingly simple, isn't it?
It is.
If even a tiny bit of fluid remains, the balloon won't fully collapse. And if it's not collapsed, trying to pull it back through that tiny biopsy channel of the endoscope is going to be a real problem.
An extreme unsafe resistance. You risk damaging the scope or, much worse, the patient. It's a guaranteed struggle.
Safety is just guaranteed by meticulous preparation.
And it concludes with that mandatory complete deflation.
So if we synthesize the core knowledge points for the listener here, it really boils down to a few major takeaways.
I'd say so.
First, that dual sizing requirement, knowing your starting size, but always having at least 3 incremental sizes higher ready to go. Second, the technical innovation of the CRE balloon, where metametric pressure equals size.
The key relationship.
And finally, the whole safety philosophy around air. The two distinct expulsion steps, one for the syringe, one for the catheter, to guarantee accuracy and patient safety.
Those are the bedrock principles of a successful setup.
That attention to detail is just. It's the difference between a successful procedure and a dangerous complication.
It really is.
It shows that this high-tech medicine depends entirely on flawless, low-tech preparation.
That's a great way to put it.
So what does this all mean for the mechanical process inside the body? We learned that pressure dictates diameter in these CRE balloons. Given that precise relationship, here's a thought for you to mull over. If the manometric pressure is designed to achieve, say, a 7 mm diameter, how might variables like significant scar tissue density or the unusual stiffness of a radiation-induced stricture, how might that interfere with the mechanical expansion?
That's the real-world challenge, isn't it? The balloon might hit the target pressure on the gauge, but if the surrounding tissue is just unyielding,
The pressure has to go somewhere.
right, that internal expansion pressure might translate into much higher shear forces on the stricture walls than you anticipated. The balloon always acts on the weakest point.
Which might not be the tissue you actually intend to dilate.
Exactly. The human element of flexibility, or lack thereof, is the ultimate variable in what is otherwise a purely mechanical process.
Something to consider. We hope this deep dive into the technical setup of esophageal dilation was useful.